I don't mean to alarm you, but I want to brace you to the fact that in this video we will be discussing perhaps the most conceptually infamous property known in the chemical engineering curriculum. That is the idea of fugacity. If you Google fugacity, you'll find that this is the subject of many memes that try to explain what it is. Kind of similar in the same vein to entropy, a lot of people have tried to define fugacity in conceptual terms and failed, in my opinion, but I'll attempt to explain it to you the best way that I know how. Which is to not even approach it to begin with. Let's just treat it as a mathematical property that we're going to use to solve problems, and then we'll worry about a conceptual definition later. So what I want you to know about fugacity is that it is similar to all the other thermodynamic properties that we are going to study, and it is no more than a tool to model vapor-liquid equilibrium. Liquid equilibrium. And we are going to use this as a tool instead of Gibbs free energy, because in the last video I showed you that Gibbs is not convenient to use because it is very sensitive to changes in pressure for the vapor phase. Very sensitive. Sensitive to changes in P for vapors, and insensitive for liquids. Insensitive to changes in pressure. I can't spell today. Insensitive to P changes for liquids. So these two things coupled together means that it's not the best property to use. So what fugacity is, instead of modeling Gibbs free energy, fugacity, you can think of it as modeling like the departure function for Gibbs free energy. So in the last video, that Excel video, I showed you that we can model what the change in Gibbs free energy for an ideal gas is. And remember that dG for an ideal gas isothermal process was V dP. And when we express V as RT over P, we got that it was RT dP over P. And we can mathematically express that as RT ln of P. So this is the starting point for the definition of fugacity. So fugacity has the symbol of a lowercase letter f, and it has units of pressure. So the other thermodynamic properties like Gibbs free energy has the same units as energy. So it's energy per mole if it's molar Gibbs free energy. Fugacity will have units of pressure. And that's helpful because, as we'll see, it gives us a better way to contextualize. So this is what the definition of fugacity, mathematically how it's defined as dG, designed so that it mirrors this expression, is RT d ln of f. Now, when we take the, oh, wait a minute, I'm sorry, this has got to be d ln of p. Right, there we go. Now, if we take the departure function, so that is the change in Gibbs free energy minus Gibbs free energy star, it's equal to RT, that gets factored out, d ln of f minus d ln of p. And my parentheses are all over the place. Okay, I think that's good. Now, a property of logarithms is I can, whenever I'm subtracting a property that's a logarithm, I can make it a fraction. And I can then solve for that fraction. So ln of f over p. Solving that gives me Gibbs of the real state minus Gibbs of the ideal state over RT. All right, so this is the working definition of fugacity that we'll work with for a while. Notice how it's like a departure function because I've got this G minus G star here. So I want to note that as our ideal assumption becomes more valid, so if we can assume ideal, then G minus G star will then be 0 because G will be equal to G star. G equals G star. And what happens then? Well, then we have 0 in the numerator of this function. we have ln of something is equal to 0, and the only way that's true is if ln of 1 is equal to 0. So if we can assume ideal, the fugacity goes towards the pressure. And this is what I mean by it's more useful to contextualize. In the past, when I talked about departure functions, I said that whatever the value of the departure function is, the larger that value is, that tells you that the more you are departing from ideal behavior. So say that I calculated that the departure function of enthalpy was something like minus 2,500 joules per mole. We might say, well, okay, that seems like a large number, 2,500, but how would we really know? I think joules per mole is a more conceptually difficult property because we don't work with that in everyday life. So if I just calculate what the departure function is, it doesn't really give me a measure of whether or not it's large or small. In contrast, if I plug this into this formula and I simply compute this right-hand side and then calculate what the fugacity is, if my fugacity is equal to P, so say my pressure was 2 atmospheres or something, and I get a fugacity that is 1.9 atmospheres, that would tell me that my fugacity is close to my pressure and I'm pretty close to ideal. So comparing, the point of this is if I compare F to P to get quick sense of how valid the ideal gas assumption is, of validity of ideal gas assumption. All right, so that's just one example of how using fugacity is better than using Gibbs. And as we'll see, it's less sensitive to changes in pressure. You don't get these wildly different answers for just slightly different pressures. Okay, the equilibrium criteria that we used before was that at equilibrium, we said that the Gibbs free energy for the vapor must be equal to the Gibbs free energy of the liquid for equilibrium. However, this was our old equilibrium criteria. And doing it that way got us an approximate equation, right? So starting here got us to the Clapeyron equation, the Clausius-Clapeyron equation, but we said that those weren't as accurate because there were a lot of assumptions that went into those, and those are approximations. So instead of using Gibbs free energy as our equilibrium criterion, we're going to use fugacity. And because fugacity was derived by looking at Gibbs free energy, we can use this as the new equilibrium criteria. Is the new equilibrium criteria. So now instead of starting with the Gibbs free energy must be equal, we can start with the fugacities of the liquid and vapor phases must be equal. All right, so let's back up and get an expression for the departure function of Gibbs free energy, G minus G star. Calculating G minus G star. And let's start by saying that G is equal to H minus Ts, and G star, these are all molar properties. G star is H star minus T S star. So then if I subtract these, I get G minus G star is equal to H minus H star. We'll put that in parentheses. And minus, the T can be factored out, T times S minus S star. Now notice what we have. We have the entropy departure function there, and we have, I'm sorry, did I say entropy? I meant enthalpy departure function here. And we have the entropy departure function there. So all I'm going to do is departure function. So now all I'm going to do is plug those already derived departure functions in. So I've showed you the departure function for enthalpy maybe last week, and then this week's homework, I asked you to derive what the entropy departure function is. So if you haven't turned in your homework for this week, I'll give away the answer as kind of a reward for watching the videos on time. So I'm going to plug all this stuff in to our definition of entropy from there. So I'm going to start with ln of F over P is equal to 1 over RT, and then plugging all this stuff in. So I need to substitute in my enthalpy departure function and my entropy departure function, S minus S star. All right, so going back in my notes to find my entropy departure function is equals 1 over RT. And h minus h star was the integral from p is equal to 0 to p is equal to p. V underbar minus t dv dt at constant p times dp. And I need to close my bracket there. Plus, it's a plus because the entropy departure function is negative. So plus, so you have a little bit of work left to do in deriving this. This t is the same. My departure function for entropy is a minus, which already comes back out in making this a plus. I've got the integral, too many brackets, integral from p is equal to 0 to p of dv dt at constant p minus r over p dp. All right, let me just give this a once over and double check, make sure I didn't make any dumb mistakes. I think that looks good. All right, so I'm going to distribute no, I don't want to distribute. I want to just simplify this now. So let's look and see what I've got. I've got two integrals with the same integrating variable, which means I can put them together. And I've got, if I put the t inside, which I can do because temperature is constant, I'm assuming, then I'm going to have a minus t dv dt at constant p and a plus t dv at constant p. So this is going to simplify considerably. So I'm going to be left with 1 over RT, and my integral now from p is equal to 0 to p is equal to p is simply this v underbar and that RT over p, because the t goes inside that integral and my dp gets left, dp is left over too. So this is ln of f over p. All right, just a couple of changes to this equation to get it into the form that you usually see it in a textbook. We can define the Greek letter phi to be the fugacity coefficient. Fugacity coefficient, and we'll say that that is equal to fugacity over pressure. So as fugacity coefficient goes to 1, that will give us ideal behavior. As fugacity coefficient is equal to f over p. And then we can also express all this stuff inside this integral in terms of the compressibility factor. So instead of v over rt minus 1 over p, we can simply say this is z minus 1 divided by p. All right, so the form that you may see in your book is ln of phi is equal to the integral from t is equal to t and p is equal to 0 to t is equal to t, p is equal to p of z minus 1 all over p dp. So this is one form, and then notice that when I did this derivation, I used the departure functions of enthalpy and entropy in terms of integrating with respect to p. So remember, I can also have another form of the departure function. And I also want to take this time to point out a significant mistake that's in Sandler. So in your textbooks, note this. In Sandler, this is equation 6.4 dash, let me double check, 6.427, correction. I think this is a significant mistake in the Sandler textbook. So S minus SIG is how they write it, or S star, is equal to, it should be equal to, they forgot this term out front. It's R ln of Z plus the integral from v is equal to infinity to v of dp dt at constant v minus r over v bar dv. All right, so make sure that you highlight this and input this into your book under Sandler 6.4-27. But anyway, I can derive an analogous expression for this ln of the fugacity coefficient by using the departure functions in terms of dv instead of dp. And that will get me the following. ln of phi is equal to z minus 1 minus ln of z plus the integral from v is equal to infinity to v of 1 minus z over v under bar dv. So I skipped the derivation of this one, just like I skipped the derivation the other time. I want you to have a knowledge of where this comes from, so carry out an analogous analysis, but instead of plugging in, when you do this step, this h minus h star, instead of plugging in the departure function with respect to dp, again, plug in the departure function with respect to dv, and it should get you to this point. All right, I know that you probably have very significant questions on what the practical use of all that is. I want to stop here for today. So I just wanted to introduce the idea of fugacity, get you an appreciation for how conceptually confusing it is. And we'll start off next time with using an example calculation where you see where this stuff is directly applicable.